very much, Juan.
Welcome.
Okay, so it's time for questions. I think already a few questions pop up here in the chat. Please keep asking. Let's start with the last question posed, which is for Jorge, the astrophysicist. Let's see, from Carlos Hernandez. How can future observation of dark matter profile in dwarf galaxies and lensing improve constraint on dark matter? Could this new observation really improve our current knowledge, or we are approaching a situation where cores and the current paradigm will become simply better established? And then that's one question. Then I guess there's another question, how pulsars could help in a context of fuzzy dark matter? Okay, let's start with the question for Jorge. Jorge, you want to take this question?
Okay, I will do my best. So how can the course of dwarf galaxies constrain the nature of dark matter? I would probably I did not read properly enough, but the idea is that I am very positive about that at this moment. And the idea is that when you go to very, very low mass galaxies, we know what is the amount of energy that the stars are able to produce per unit mass. We also know what is the dark matter halo that corresponds to these very low mass galaxies. And so we can, as a back of the envelope estimate, see what are the masses at which the energy that stars are producing can no longer modify the gravitational potential in dark matter, okay? And we are currently reaching that limit. That limit is slightly model dependent, but not much. So probably if we manage to really observe in detail dwarfs of the order of 10 to the 5 solar masses, stellar mass, we will have an answer for that. So I'm very positive about this thing. I don't know whether I answered the question. Well, to some extent I did. So how can pulsars help to constrain fuzzy dark matter? I don't have an answer for that. Maybe some other of the panel want to answer that thing.
I was going to move to another question because we have many. So for a particle physicist, so for Maria Luisa from Juan Miro, how do we know that dark matter particles are stable or long-lived? Since at the same time, we're looking for decay products when we're trying to detect dark matter indirectly.
Okay, so thank you. Of course, if dark matter is explaining the dynamics of the universe, it should be still present, but we have to have a mechanism for production in the past of the universe. So we have to explain the genesis of the dark matter particle, but we have also to have these particles now in the universe. So this means that the particle has to be at least with a half-life comparable to the age of the universe. That is not the same that stable. Because very long lives are allowed. And in this case, we could look for decay of these particles in the galactic halos. Part of them will be decaying, but not all of them. This is just a question of the lifetime assumed. But if it's stable, of course, there won't be decay of dark matter particles. Because of that, all the searches I have commented are strongly dependent on the particle properties. And we really have no idea. We have only limits for the properties. We can say which lifetimes are not possible, but not to say that it's stable or not.
Thank you. Then there is a question from Benjamin Montesinos to both Juan and Maria Luisa. So I guess probably Juan can take this one. In February of this year, a paper was published in which the authors say that the strongest detection of gravitational waves could be the aftermath of the collision of two stars made of axions or made of dark matter. So what is your opinion in the context of the hypothesis that both of you speakers have outlined? And would it be consistent with the scenario in which dark matter is partially composed by black holes and partially by particles?
Well, it's an interesting question indeed. Now, let me qualify it, because there was no claim that it would have been due to dark matter particle, or for instance, like an axion. You need to invent a new object, which is it's a gauge field. It's a gauge particle, not a scalar, and it has to have a special mass and coupling. And in some cases, those new boson stars may form. That is something which is very difficult to do. I think one of the authors in the audience, he might explain it to us. In the early universe, with sufficient abundance that they would find each other and finally merge today. Now, of course, you have to have very special initial conditions for that collision to happen. It has to be head-on. Some of the properties are very contrived. I don't think there is clear evidence that such a collision comes from such a particle. But let me answer differently, whether, so the second part of the question, whether it is possible to accommodate a dark matter scenario which contains both primordial black holes and particle dark matter. It is possible. For the moment, there is no inconsistency. It would require some coincidence in the time of formation, or its coupling to the rest of matter, because the way you produce dark matter in the early universe and how it freezes out and produces a certain abundance today is very different from the way you compute the abundance of primordial black holes from the gravitational collapse at a given time. So you would have to make a certain coincidence problem here between the nature of the dark matter particle and the mechanisms of gravitational collapse. It's more natural that either or would be valid, but there is no clear indication against it, right? Just like we know that baryons and dark matter have a similar abundances today, a factor of 5. No? It could be that there is something like that, about factor 5 or 10 or 100 between one and the other. Okay, but I think in the future, constraints on particle dark matter will be even more stringent than today, and the same will happen with primordial black holes. And therefore, we should be able to answer that. Now, taking the opportunity of these constraints to take another of the questions of Benjamin and other members of the audience, it's important to clarify that the standard constraints on primordial black holes assumed that the black holes were distributed uniformly and had a single mass. It's called a monochromatic and uniform distribution. Now, once you relax that assumption and you accept for a broad distribution, for instance, black holes at a few solar masses, 100 solar masses, 10 to the -5 solar masses, 10 to the 6 solar masses, once you accept that there is some mass distribution and that they could be clustered, forming these clusters that I was mentioning before in my talk, then it's natural to evade, it's very easy to evade those constraints, which mostly come from microlensing experiments. So you change the optical depth to, for instance, the LMC, and from CMB observations, which, at least in the mass range that I'm discussing from Ligo Virgo, so in the mass range of 100 or so solar masses to 1 solar mass, there the constraint from the CMB, which would have injected energy pre-recombination into the plasma, can be evaded, since the only constraint we have there from the spectral distortions come from COBE, which gives only 1 part in 10 to the 5. In the future, possibly with PIXI and other experiments, we might be able to detect the primordial black holes precisely because of their injection into the plasma, or put very, very stringent constraints on them. They might reach 10 to the -8 in amplitude for those energy injections. For the moment, they are consistent with observations. In fact, there are some observations, like those of Ogle, that suggest that there must be a component, particularly in the planetary mass range of primordial black holes. But that's an issue that we can debate on. And I stop here.
Thank you, Juan. So let's go back to the astrophysicist. A question for Jorge. What do you think of the Mond theories of modified Newtonian dynamics theory as an alternative to the existence of dark matter? Very important question.
Okay. First, saying that from the beginning, we decided that we were not going to try to address another possibility to solve the need for dark matter, which is, I mean, basically what happened from an observational point of view is the fact that the luminous matter doesn't have enough gravity to explain the motions. This you can solve, as we have been discussing here, through assuming that there is an extra component that we don't see. It's not producing light, but it's creating gravity, so dark matter. But the alternative is simply saying that the gravity, as we know it to be, doesn't hold for galaxies at this scale. So you have to change the gravity. And this is a possibility that is always there. But we decide from scratch, from the design of this presentation, that we are not going to enter into this other discussion, which is extremely interesting. It hasn't ruled out at all yet, but it's slightly different. Now, once I've said this thing, I can say something about MOND. MOND is a phenomenological theory that says that, that you have to modify basically the gravitation when it reaches very low levels of accelerations, and is able to explain some features of the rotation curves of galaxies. Now, I'm not an expert in MOND. I'm an observer. But the impression that I have of hearing people that knows about MOND is that he does very well to deal with objects like galaxies, which is precisely where it was introduced. This is the field where it was introduced, but it's not so well. I'll try to explain many other things that dark matter theory explain, like the formation of the structures from the forming structures with the fluctuations that are observed in the CMB, with the time scales that we know that the universe has, the age of the universe. So MOND doesn't do very well at that, at least hasn't been shown to do as well as the lambda CDM. But this is not a competition between the two things. So from scratch, this is an option, it's there, but this is not about this other possibility.
Okay, thank you, Jorge. Let's move to a question for Maria Luisa. What fraction of the space parameters of potential dark matter particle candidates has been searched so far? Is it a tiny fraction or is it a significant fraction?
Okay, so I will say that this is difficult to answer because we have not think about all the possible candidates. So we have moved always in some proposed models for particular candidates as actions. And for actions, there is a part of the parameter space that has been explored. And now experiments are approaching to the most interesting region of the parameter space, for instance. But for other candidates, we don't have really a very well-framed for the properties, for the mass and cross sections that are possible for those candidates. And then I will say that maybe we are really very, very far from the region where the particle can really realize their properties. And so I will say that really now, after results from LHC, for instance, the supersymmetry has really become a little more or less plausible explanation from the beyond the standard model physics. We have really too many models and too many possibilities really to say which is the parameter space we have to search for. It's difficult.
Okay. Thank you. Let's move to a question for the cosmologist, Juan, from Jose Diego. So, is the spin distribution observed by Ligo consistent with the primordial black hole hypothesis?
That's an excellent question. Okay, so indeed, we are used to the gravitational collapse of a ball of gas by conservation of angular momentum to end up into a compact object which is spinning. We see this in neutron stars. We expect that for black holes, and indeed, all of the black holes that have formed from stellar evolution are spinning. Now, that was something that shocked the community when the gravitational wave detections of the spin of those black holes didn't show any spin in the components before the merger. Of course, the final merger had a spin which was consistent with what you would expect from a conversion of angular momentum into a spin out of the merge. So is that a hint that those black holes had to be primordial, or is there a way in astrophysics to shed away angular momentum as gravitational collapse leaves behind a black hole? That's a question which astrophysicists have tried to address. They are extremely complicated numerical simulations. For the moment, there is no evidence of any, so for instance, by implementing magnetic fields or some other mechanism to get rid of angular momentum and leave a spinless, really without any spin. Some of the measurements clearly show that the initial component of that binary had no spin at all, zero. It's very difficult for these to be generated. And it's more difficult statistically, I would say, because you might say, well, perhaps 1 in 1,000, 1 in a million of those gravitational collapse leaves behind a black hole without spin out of stellar evolution. Now, what is rare, and this is something that I have studied with my group here in Madrid, is that all of the binaries that have been seen in both the round 1, 2, and now in round 3, all of those have 99% or 90-something% of them have progenitors without spin. Okay, so you would expect it at least say half and half or so. So that so many of them have no spin might be a hint that some, if not most of them, are primordial. Apart from their mass distribution, okay, I want to insist here. A clear clue would be to see black holes where you don't expect any, right? Like below Chandrasekhar, limit in the mass gap, lower mass gap, and the upper mass gap. But the fact that this comes together with the fact that there's no spin seems to be another hint onto this. I think this is relevant. Another question that was posed was about how would this mass distribution, it connects with the question that was posed now, how the mass distribution can be obtained in a natural way. And for this, one requires some dynamics during inflation. Remember, I was saying about the primordial plasma. Let me share very briefly one slide. That in order for those black holes to form, you needed the radiation pressure to be not enough against gravitational collapse. Now, it happens that in the evolution of the universe, and this connects with particle physics again, in the early universe, we know that there were more relativistic particles. As the universe expanded, those relativistic particles became non-relativistic, like the C boson, the W, the Higgs, the top. No, they became non-relativistic, more or less at the electroweak phase transition, which meant that those degrees of freedom suddenly disappeared from the plasma. They no longer contributed to pressure. Now, one of the deepest drops in the loss of pressure comes from the moment where quarks and gluons, which were relativistic at 200 MeV, suddenly condensed to form the protons and neutrons. At that time, 80% of all the relativistic degrees of freedom disappeared. You see this sudden drop in this image from 80 to about 10 or so degrees of freedom, suddenly drop and disappeared from the radiation pressure. So that means that whatever fluctuation which was there, which trying to collapse the plasma, was not prevented from collapse at that time. So it made it much more probable for those black holes to form at that time. Out of all possible horizons or domains where these black holes could form, a few of these had a larger probability of collapse. This means that the mass distribution should be peaked around that scale. And that's precisely where our model proposed that there should be a very dominant peak at around 2 solar masses. This has to do with the size of the horizon at the time of the QC transition. But that's not the only place. You could also wait until the universe has cooled down so that E plus and minus annihilates. And that time, again, electrons and positons disappear from the plasma. There you have very few degrees of freedom. So you have a significant decrement in the radiation pressure. Again, allows for the production of black holes. So you have a spectroscopy of black holes. And this is where, apart from spin, I would suggest we should look for. We should look for correlations in the masses of those black holes to have a hint as to what kind of model could be behind the production of these black holes.
Okay, thank you very much, Juan. Let's move to a question for the astrophysicist. So Jorge again. The question is from Ana Luisa. She asks, if the dark matter is proved to be not hot, neither cold, given the current tension with the Landau-CDM model, could it be warm? And what does that mean? What would it imply? Well,
again, maybe if the answer, if the question is what is warm dark matter, probably I'm not the right person to answer. But what I can say is that warm dark matter is considered among the possible ways to solve these small-scale problems of the lambda CDM. And indeed, it produces cores and even to some extent solves the problem of the too big to fail. So it has been considered and it solved the problem. Now, if eventually we find out that the dark matter is not cold, then the next step would be to try to see what of the various possibilities is the one that that really explains the dark matter. But so far we are still at zero order, trying to decide whether it is cold or not. So yes, the warm dark matter could solve some of the small scale problems of the cold dark matter model, but whether it is better than other ways of solving it, I don't have an answer for that yet.
May I maybe add something on this topic, Jorge?
Sure.
Don't mind. So the issue with warm dark matter is that it's been shown that in order to form cores, you need a dark matter particle candidate that is warm enough. But the warmer it is, the more it cuts off the power spectrum at small scales. So you reach a point where basically you are just impeding the creation of dwarf galaxies on a first place. So there is some tension. So in order to form cores in dwarf galaxy, you want a really warm dark matter candidate. But if you have a really warm dark matter candidate, you can't produce those galaxies in the first place. So I think that there is some small window of constraint for current warm dark matter candidates, but it's not so easy to solve at the same time, for example, the Caspian core problem and the number counts of objects that we observe at small scale. There was something that I heard about, let's say. Okay, let's ask another question to Maria Luisa. Let me find one. I just found one over here. Actually, again, from the same person, from Anna Luisa. Can the graviton be related to the particle dark matter candidate?
Well, I maybe after can say something more about this, Juan, but I will say that the graviton is massless, and I wouldn't expect that that is related in any way with the dark matter problem, but I'm not an expert in relativity.
I agree with Maria Luisa. Indeed, the graviton is relativistic. So there were some speculations. I think it was, well, never mind. I think it was Wheeler, who thought that you might produce condensates of gravitons, like a ball of gravitons, geons or something like that, I think he called them. And this condensate would not be relativistic, okay? They would be formed in the early universe, and they would behave like a Bose particle, right? Rather than having spin 2, they would have spin 0. In that case, you might envision some kind of Bose star out of these. I find this really far-fetched. Not only the interactions would have to be very peculiar, the mechanism by which they were produced would be in the early universe, probably before inflation, they would have been diluted. So it is, I think, as a possibility, is not completely ruled out. It's simply very implausible.
Okay, let me then ask another question to Maria Luisa that I was just thinking about. So why, I mean, the broad question is, why haven't we found dark matter yet, either via direct or indirect detection? Of course, it's difficult, we know that, but it brings me to a similarity with the search and discovery of gravitational waves. After many decades, people were almost losing hopes, and we're always blaming detection limits or whatever, seismic noise, and finally they observe gravitational waves. What's your view on this? Are we making progress, or?
Yeah, so for sure we have been making a lot of progress in the detector technology, and so these detectors can be applied also for other things. So the main question is that we don't know really which particles to look for, and then it's really very difficult to design a very focused detection strategy if you don't know what you're looking for. So in principle, for indirect detection experiments of observations, I will say that they are not dedicated experiments for dark matter. So they are searching for cosmic rays, for gamma rays, for neutrinos, and to do neutrino astronomy. And so they can learn about dark matter, but because these messengers can bring information from dark matter. But in the case of direct detection, so we try to explore the part of the candidates that we are sensitive to. And really this has experimented an incredible increase in sensitivity in the last 25 years, so several orders of magnitude. So now we can say what dark matter is not made of. And I think that this at least is an answer, but maybe not the better answer.
Okay, because in the gravitational waves community, people were blaming sensitivity, but at some point, the skeptical were starting thinking, well, maybe there is no gravitational waves.
Of course, but but most of the people was convinced that that gravitational waves exist. In our case, it's not so clear. So maybe we are looking something that is not there.
Okay, thank you. A question for the cosmologist, Juan, and perhaps even for the astrophysicist, Jorge. Let's start with Juan. So, question from Nacho Trujillo. Why we do not see many micro AGNs produced by primordial black holes colliding with large gas clouds in our galaxy?
Again, it's an excellent question. Actually, we may have seen them. The question is, do present observations in X-rays and gammas clearly trace what is the progenitor? Some cases, you've seen the mass distribution that we have in our scenario. So you have black holes that go all the way from below solar mass to several hundreds of solar masses. Some of these black holes, which would be lurking in the halo of the galaxy, might encounter sufficiently dense environments where there is gas. And this gas could be in the form of stars, could be in the form of molecular clouds. That gas will inevitably interact with the black hole. Typically, small black holes would have very little cross-section, would not tend to form these micro AGNs. But there are, as you know, microquasars in our galaxy, famous Binabel, 1995. So we now know that there are features where events in astrophysics where stars orbit compact objects, neutron stars or black holes, and they emit in X-rays. And these have been seen with several solar masses, for each of these compact objects. So it could be that some of these are primordial. Of course, they could come from stellar evolution. So at that, I mean, in this observation, you cannot tell apart from the one from the other, except for their abundance. For instance, if you look for, and it's something which we are doing here also with Daniele Gaggero and Francesca Scaramella, is to look for evidences in dense molecular clouds of the emission in X-rays of black holes that would belong to the halo. That means that they are primordial and they're orbiting around the central black hole, and they encounter these dense environments and eventually shine in X-rays. So this would be a very nice way to distinguish this. Another possibility is that very tiny black holes, 10 to the -5 solar mass black holes, so planetary sized black holes, lurk in the outskirts of the solar system. For instance, maybe this is Planet 9 is one of these black holes, and eventually through interactions with ice, perhaps in the Oort clouds, or with some other components, might shine, and we would be able to see not only its gravitational interaction, but also its response to the presence of matter. So perhaps there are chances that we might see this in photons, in light, from direct interaction with the gas. But I would say, answering another question that was posed in the chat, that the best way to look for these in our halo is through microlensing. And indeed, there are searches I myself am part of, for instance, with the Vera Rubin Observatory, to search for microlens events in the halo of our galaxy. Actually, in all the galaxy, not just to the bulge or the LMC, but all of the galaxy, because we'll be able to monitor the light of stars very exquisitely with high cadence and with high depth. So we should be able to see these microns events if the halo of our galaxy is composed at least with a fraction of uniformly distributed black holes. If they are clustered, then, as I was describing in my talk, they would be producing a very tiny optical depth. The probability that one of these clusters goes across the light of one star would be very tiny, and its Einstein ring would be so big that the time scales for variation of the light of that star is in the decades, not in the years or in the minutes or hours, right? So you will not be able to see this unless you monitor for a century. So there are issues with gravitational lensing which are worth discussing in detail, more than what I'm doing now.
Thank you, Juan. I don't know if Jorge wants to add something about this topic. You're muted, Jorge.
I was saying that okay, I mean, it's fine, the answer, in the sense that I have comments, because I know that, I mean, the stellar evolution already produces enough black holes to explain all the X-ray binaries that are observed. Actually, most of the black holes that are naturally produced by stellar evolution are undetected. They are like moving around in the halo of the Milky Way. So there should be plenty of these dark matter halos, and people is looking for them in X-rays. And apparently, I'm not familiar with these things to the end, but I think that they are the limits of the surface in X-ray are such that not very late we will be able to say something about the population of the black holes that are produced by stellar evolution. Okay, and of course, then at the same time, they will say something about the other origin. I mean, other black holes that might be around. Now, let me take the opportunity to ask you something that hasn't appeared explicitly. So, could you comment on the? I mean, from observational point of view, what are the observational limits for the fraction of dark matter that could be due to primordial black holes? What is the current situation?
Okay, so for at the moment, depending on where the mass distribution is, it could be 100% of all the dark matter. So there is a window at around the solar mass that is probed by the Ligo Virgo detectors, where you can accommodate essentially together with the 100 solar masses and 10 to the minus 3, which are maybe a few percent abundances. Most of it would be at 2 solar masses. This would be in perfect agreement with being 100% of all the dark matter. So by clustering them, by sequestering and putting them in localized regions, you can completely evade all of those constraints. You can evade the wide binary constraints because they form a concentration, and you have a intermediate mass black hole at the center of those white dwarfs, dwarf galaxies like Eridanus. You can evade the constraint from Machos and Eros. You can also eliminate partially, not completely, the constraint from the CMB, from spectral distortions, like I was describing before. But essentially, you can put most of the masses right around those solar masses, and it would perfectly be in agreement with observations. Now, let me qualify with respect to what you mentioned about the X-ray binaries, because you will agree that if you find black holes, which are at the center, fortunately with X-ray binaries, you can measure the masses of the compact object quite accurately, at least within 5%, then you would agree that if you find a micro quasar with a black hole at the center, which is below a solar mass, that could not have been produced by stellar evolution. If you find one which has 100 solar masses, again, could not have been produced by stellar evolution, you would agree then that you're finding new components, right? Even if you can produce from stars, black holes, but not of those masses. Do you agree with that? Okay. Thank you.
Thank you, Juan and Jorge, for the question. So let me ask now a question to Jorge. We have talked, I mean, you've talked a little bit about baryonic physics. So the question I would like to ask you is, how much does baryonic physics weight against the constraining dark matter models? Like, once you include baryonic physics on top of a warm or cold or self-interacting dark matter particle, results can often be degenerate. What's your view on this, and is there a way to try to solve this degeneracy?
Okay, yes, I mean, baryon physics is fundamental because it modifies the small scale structures that you can see, which is baryons, basically. So they have to be modeled in a way that are realistic enough to be able to discard its influence on the small scale structure that is observed. Now, I think that at this point, we are having numerical simulations that are right there where you can start trusting them, let's say, to the end, okay? But so I think that, I mean, there is always an interplay between baryonic physics and other type of explanations. If you were able to model to the end the influence of the baryons, you could say something about the nature of dark matter. We are now in a moment where simulations are realistic enough to start saying something about whether or not they are producing the small, I mean, they are responsible or not for the small scale problems of the cold dark matter. Now, in addition to that, I would try to argue, I try to argue that if you go to very, very low masses, there are arguments that are slightly, that are basically independent on the modeling that will tell that, for instance, the cores should not appear in very, very low masses, independently of the baryon physics, because the baryon physics don't have enough energy to modify the gravitational potential of the dark matter. Remember that as you go to lower and lower masses, I mean, the amount of dark matter that you have per baryon increases. So it's more difficult for the baryons to modify the potential. And these 10 to the 6 solar masses seems to be at the limit where stars can do something. And this is not very model dependent. So I'm gonna say it in a single sentence as a summary. So it's critically important. We still are in a moment where baryon physics cannot be fully disentangled from the nature of dark matter, but we are not very far from that point. So that's my impression, at least.
Okay. Thank you, Jorge. Let's move on Maria Luisa, particle physics. I don't know if you want to take this question. Let's give it a try. What if dark matter is made of Planck relics? Any chance to detect them one day, or is it going to be impossible? And then someone else under it asks, and for outsider, just explain what a Planck relic is. I don't know if Maria Luisa, that's your.
No, I'm not sure to understand really what is the question. So there are, maybe refers to mass Planck, so the mass of the Planck scale for the particles. But so in principle, relics from the past of the universe could be produced, of course, in the different new physics models, and could be there in the universe. So I mean, for very large masses, if it's the question about that, of course, the distribution could be complicated, and the detection is also very specific for the model of the particle that could be produced. But I'm not sure if it refers to particles really or to other kind of relic. Maybe some of the audience know more.
Okay, before asking to Juan, maybe know something about it, let me ask you this other thing. There was a question from Jorge, actually, for both of you. How can astrophysics help you to solve your problems?
No, of course, astrophysics is fundamental to understand the distribution of the particles we are looking for. So we need observations and models for the distribution of dark matter particles, and we need to know the density of the particles in the Milky Way, for instance, for direct detection experiments, because we need the local density of dark matter, but also the distribution of velocities of these particles, because this is crucial to determine the expected interaction rate in our detectors. So, for instance, now, if Gaia is measuring really with a very large astrometric effort to understand the halo of the Milky Way, this could really improve a lot the knowledge of what signals should appear for a given candidate. So I will say that it's really very, very important to get information from the astrophysics point of view and to integrate this in our searching protocols.
Okay, thank you, Maria Luisa. And let's now move to Juan. In the meantime, the person that asked the question has clarified that he refers to microscopic black holes. So maybe Juan can... Yeah.
Let me briefly describe. Indeed, Planck relics assumes that the endpoint of the evaporation of a black hole is not Minkowski space-time, so that the singularity disappears, but something remains there. This was a discussion that arose from the information loss paradox of black holes in the 70s and continuing all the way until the 90s and 2000. Nowadays, we understand that this is perfectly consistent. If you want, the usual unitarity evolution of the evaporation of a black hole ends up in Minkowski, and therefore you don't have any relic. Now, if there would have been a relic, and this relic would have had a very tiny mass, it is true that it might contribute with a tiny fraction to all of dark matter. The main difficulty is that those black holes would not amount to enough to produce what you need, unless they are primordial, in the sense they were produced before the baryons. No? Because those black holes which evaporate, even if they started very early and take less than the age of the universe to evaporate, they would still comprise less than you need in order to explain the dark matter. We know this fraction of factor 5 more dark matter than baryons, right? So usual stellar black holes will not contribute, even if they evaporate and leave a relic, to sufficient abundance to produce all the dark matter. So you need something primordial. Now, with respect to the question that you posed to both Maria Luisa and myself about the from Jorge about the use of astrophysics for addressing some of the issues of our different approaches, I think clearly astrophysics is crucial. We live, of course, immersed in the data that comes from the outside world, and this is mostly astrophysical data. However, I have always trouble with astrophysics in the sense that the uncertainties are not those of particle physics. If you want, the Liberon, the fudge factors that you could always add to astrophysics has troubled us particle physicists in the sense that it leaves us too much uncertainty. It leaves us no definite answer for some of our questions. In particular, you might want to know whether definitely within 95 or 99% confidence level, you're sure that the spin of a compact object that ends from a stellar evolution is one and not another, or whether the mass of, again, a compact object is clearly cannot be between, say, 50 and 130 solar masses, no, in the peristability supernova mass gap. Now, all of those uncertainties are important to be resolved. That's why I think astrophysics should, in my opinion, in order to defend or contrast their ideas with the rest of the community, and this is what we're doing here, no? Trying to make these bridges between communities. It would try to address the need for precise statements, okay? Rather than, I know within the order of magnitude that such a thing occurs and such cannot occur. It is important in order to be logical, no? In order to use our scientific method, that we know for sure that there is a clear statement that thing cannot happen, because then you look for alternatives. Now, if you say that could not happen, but with 50% uncertainty, you're at a loss, because you would never be able to discard that possibility. You would never be able to say, well, it could have been that that black hole was an astrophysical black hole, for instance, just to name one thing. So I think astrophysics could help by being more precise, by having not just scenarios, but models, by having clear hypotheses which can be followed all the way to the end, where you define much better your initial conditions, you define your environment. I know it's a very complicated problem. I'm not criticizing astrophysics as a whole. I think it's necessary, because we cannot do experiments with stars. No, it's necessary that we do this hypothesis, that we put in the table, we design what are our assumptions, and we follow those assumptions all the way to the end. We do our best embodied simulations. We do hydrodynamics. We do whatever is needed. No, but it is important that we stipulate or define very clearly what are our error bars. No, otherwise it's very difficult for the other communities to be able to compensate. One example has just been measured here about the fact that you could try to resolve the core problem with some self-interaction of dark matter. There is a moment where these big uncertainties at the end rely on data on how the mass is distributed in the course of dwarfs or in the course of galaxies. And unless we know that with some accuracy, you cannot be able to respond whether a particle can answer, or you need a black hole to answer the question. So your question brought together a whole, if you want, more philosophical discussion of what is the reliability of a science, no? And I think this is important. The reliability of theoretical physics and reliability of particle physics is perhaps not as it's not compatible to that of astrophysics, and it would be of enormous help for our communities if such a reliability was firmly established, no? So we could make statements with it.
So Juan,
I stop here.
Thanks a lot. We have actually a few more questions for you, but I see Jorge wants to reply something.
Well, it's not a reply. It's simply trying to, I didn't try to be philosophical in my question. It was something very specific. Do you have astrophysicists in your daily life? So in your,
yes, of course.
Among in the teams?
In my group,
you are
we have
working together?
astrophysicists. Yes, of course.
Because many of the problems that you mentioned, to me, sounds very much like a problem of communication. Very often, I mean, the uncertainties are not clear because the jargons of it, I mean, whether you are an astrophysicist or something else, the jargon that you use is different. So maybe most. Well,
oh, no. It's much more specific. Let me see clear. No, I talk to astrophysicists. For instance, can you tell me how sharp the boundary is between forming a black hole or not at, say, 60 solar masses? And your answer will be, no, I have no idea. It could be 50 or it could be 70.
Yeah, but probably that's the answer. So, and you have to live with that. So it's something that, I mean, if you need that information to advance, then you have to move to a different question or a different answer. Because, I mean, observationally, there are limits that you cannot go beyond that thing. So what I'm saying, but I don't want to try to be philosophical. The question was about really whether we can think of a specific works that we can do together. When I say we, it's not you and me, it's the community. So if you need an astrophysicist, the natural thing is that you team up with them. So you incorporate an astrophysicist and vice versa. And the same for Maria Luisa. So do you have astrophysicists in your team? You were talking about the halo of the Milky Way and the need to have a detailed description of the halo to predict the signals to be expected. Do you have astrophysicists working together?
No. In general, from the direct detection point of view, what is assumed is the most simple halo model, because it's the most simple to derive limits. And up to now, there was no more real data on the Milky Way galactic halo. So we assume isothermal and isotropic distribution of velocities at the rotational velocity in the position of the sun. And then we do the estimates of the rates with this very, very simple model. Now, with Gaia results, then it starts a little more to move to other possibilities for the distribution of the particles in the proximities of the sun. And then maybe we'll change the interpretation of the experiments. So the problem is that for calculating the expected rate in our detectors, so it's really very important to know the velocity of the particles, the directions of motions, the possibility of streams of the dark matter particles in the halo. And there are a lot of uncertainties that are difficult to use, and we have to do all the experiments the same approach in order to compare our results. Because if one group takes one halo model and another group takes a different one, then our results won't be easy to compare, because all the uncertainties will go to the result. So it's really quite a complicated methodological issue, the interpretation of our experimental results in this sense. So
yeah, I think if I can add to the discussion, this is a very important point. I mean, there are, from the astrophysics point of view, like I work in simulations, for example, there are more and more simulations showing that the dark matter halo of the Milky Way is very contracted toward the center, and that will change also your expectations. So it's important to really talk within the different communities and try to. Okay, so there is a few more questions. The time is almost over. Let me ask one to the cosmologist, to Juan, a question from Jorge Kamalic. He asks, how difficult or natural is to model a suitable primordial black hole mass distribution function that evades all the bounds and searches and explain dark matter?
It's an excellent question, which I briefly outlined before. Let me try to show, to share a screen, because I prepared for that question a slide. Okay, so let me share. Do you see the slide?
Yes.
Okay, so remember what I was describing before about the thermal history of the universe. It is natural in the sense that we're not introducing any new ingredient. The only assumption is that there is a background of fluctuations introduced by inflation that is similar to the background we observe in the CMB, only larger in amplitude. It's natural even in single field models. Even the Higgs can do that. If you have a non-minimal coupling of the Higgs, this produces this extra plateau. Now, once that's the only, if you want, assumption of the model. Once you take this, just the thermal history of the universe, the fact that the universe expands as it cools, where different thresholds of masses are reached inevitably, and you form the structure like protons and neutrons. At that time, inevitably, those collapses will occur. This is Hawking and Penrose's theorems, right? So in the presence of that plasma, the black hole would inevitably have to form. So the question immediately is, fine, if this happens, what are the constraints? Can we evade with this shape of a mass function? Can we evade all of the constraints? And the answer is yes, indeed. You can, by understanding of the formation of black holes come together with their clustering, you can introduce, through clustering, the required ingredients for the agreement with all the observations. on the left of this peak, where you see it's almost 100%, this would be 100% of all the dark matter made of black holes. To the left, you have most of the constraints from microlensing. And indeed, they evade them. There are some indications that at 10 to the minus 5 solar masses, related to the electroweak, there might be some microlensing events, particularly towards the to Andromeda and also in the bulge by the hypersuperine CAM and by Ogle, which seem to suggest that there is an excess of events that you would expect from the halo, that which could have been by objects of 10 to the minus 5 solar masses. Of course, whether they are planets or black holes, it's another matter we would have to resolve. No, if some of these are sufficiently nearby, you might try to see whether they emit any kind of radiation. No, but otherwise it's difficult. So it could be that we are beginning to observe the shape. Now, on the right hand side, you have constraints from the CMB, you have constraints from dwarf binaries, you have constraints from other phenomena, which, given the sharpness of the fall, are in agreement. Now, small variations in this flat plateau, you make it slanted or you make it curved, just like you do in the CMB fluctuation with some running of the tilt or some tiny tilt, are enough also to evade the constraints on large masses. Otherwise, this would be slightly too high. And in fact, very interestingly, people like Günther Hasinger, astronomer, has explored what are the consequences of such a scenario, and finds that it's natural in that context to generate the intermediate mass black holes at the centers of some dwarf galaxies and the supermassive black holes at the centers of all galaxies in this scenario. So in a natural way, this what we proposed here 2 years ago, it seems to accommodate all the observations and all of the dark matter in the form of black holes.
A lot, Juan,
Thank
and
you.
I think being 1 o'clock plus 1 minute, is about time to close the event. So I would like to thank all the people that have made it so far. I see about 60 participants. And I'd like to thank especially our 3 speakers, and in particular Jorge, that was really the mind behind behind this event. So thank you, Jorge. And of course, thanks to the SEA organizer to give us this opportunity to share, our view on such a broad topic that we hope was of interest for the community. You will find the recording of this session in YouTube, I believe, soon. And that's it. So Jorge is reminding me that anybody that is interested to speak with them can directly contact the speakers via email, and they'll be happy to respond. So yeah, thanks everybody, and let's go for lunch, I guess.
So
Bye.
no, bye, and thank you very much.
Thank you all for coming.
Congratulations to the organizers, and we have learned a lot from listening to you, and thank you very much. It was extremely interesting. Thank you.
Gracias a todos.
Thank you for
Thank
being
you.
here. Take care.
Thank you.
Bye-bye.
Thanks, bye.
Bye.